another edition of the Finite Element seminar at Lawrence Livermore National Lab. Today it's my pleasure to introduce Denis Ridzal from Sandia National Lab. I've known Denis for 12, 13 years, maybe more now. He got his degree from Rice, and then he went and was the von Neumann postdoc in Sandia, big honor, and spent the rest of his career there, probably almost 20 years at this point. I don't know.
Yeah,
close.
that's right. Yeah.
He's an expert in optimization. He has the rapid optimization library, the ROLL project. It's software that he's leading. And today he's going to tell us about his work on adaptive methods, but not for improving quality, for improving memory and compression, which is, I think, a very interesting and relevant topic for us. Denis, thanks for agreeing to present. The floor is yours.
Thank you, Sandia, for the kind invitation. First, I would like to thank my collaborators, Graham Harper and Tim Wildy from Sandia Labs. This project was sponsored by the Lab-Directed Research and Development Program at Sandia. It was a short 2-year project, but I think we got some insights, important insights that I would like to share today. All right, so a little bit of history first. Why did we go down this route? So about 4 years ago, we were working on a project where we're trying to design electromagnetic systems. And the goal here, and this was a DARPA project, the goal was to replace some of the optical systems for night vision goggles with lightweight and shorter length scale systems. And the way they were going about it was to replace some of the optical elements, such as lenses, with so-called meta surfaces. Just a quick question. Can you see my pointer? It's important that I can point.
Yes, we can.
Okay. So here's an optical stack in, let's say, night vision goggles, and consists of a bunch of lenses. And we wanted to replace some of those heavy and thick elements with very, very thin surfaces for obvious reasons. Weight savings, shorter length, less torque on the neck of the wearer, and so on. Now, what are these metasurfaces? Well, they are electromagnetic devices with nanoscale structures. And I have a picture here on the left of one of them. This is just a very small scale model. They're micron thin. They contain millions of so-called meta atoms, and you can see them here. They have various shapes and sizes. And the unique feature about this is that if you look at, for example, one of these meta atoms, is that they are all extruded in one direction. And so what some of the folks on the project noted very quickly was that whenever they could mesh some of these, or whenever they could use finite difference methods for the simulation of these metasurfaces, and that was possible for, let's say, square shapes and such, the performance was not only much better in terms of speed, but the memory use of commercial tools, finite difference tools, was at least an order of magnitude better than our finite element simulators. And so they could run much, much bigger simulations with those tools versus our finite element methods. And so that motivated us to think hard about, memory use, and also the types of meshes that are used in this applications and others. And so in this particular application, we have these extruded meshes, and you can imagine that there is a lot of repetition in terms of the cell shapes. And we wanted to benefit from that on the memory side. This is important because not everyone has access to very, very large-scale computers, and even those can run out of memory quickly. And so here are just a few remarks on where we are with memory use. Modern computing has embraced massive concurrency. Now we have million-way concurrency in many scientific applications. Frontier and Aurora are already running exascale calculations, but many applications requiring the numerical solution of PDEs are not limited by the speed, by the sheer speed of the system, but actually by the system memory. And this is really due to what I would describe as reductions in the amount of system memory per thread over the last 10 or so years. And so new approaches are required to address this challenge. And I should just note that, a lot of people are trying to use neural networks to replace parts of PD simulations. Well, that won't really help, because in order to train the neural networks, you still have to run these massive simulations with all the memory restrictions that they have. All right, so I think there's quite a bit of hope here, and I think one of the fundamental shifts over the last 10 to 20 years is really helpful here, and that is that most HPC applications based on finite element methods use modular libraries now. No one develops things from scratch. And so whether it is FEM or DEAL2 or Intrepid at Sandia, we all use libraries. And so the community here has an opportunity to address this memory challenge at its source, or a source, which are the data structures that are used for finite element computations, and to do so without significant changes to the implementations of these applications. So if you can kind of do things underneath the hood to reduce your memory footprint, the applications will automatically benefit. There's a little bit of a twist here, which I may get to towards the end of the talk, and that is that also mesh databases that we use to track just the mesh data have to sort of come along. But I think that they will join the effort if we're successful in reducing the memory footprint on the finite element computation side of things. All right, so just very briefly, some related work. We are probably all aware of matrix-free approaches such as Jacobian-free Newton-Krylov methods and FEM's partial assembly. They all seek to avoid storage of Jacobians of P residuals, and then use matrix-free matrix-free methods for linear algebra, so matrix vector products instead of matrices. Of course, that has to be accompanied by the construction of matrix-free preconditioners, which is a challenging task, and there's quite a bit of research that is going on in that area. And there are just a couple of references on matrix-free multigroup preconditioners, such as those by May Brown, etc., and Clevenger and Heister. Now, there are a few other related efforts. One is well known in the finite element community, and that is sum factorizations. The sum factorizations try to reduce the cost in storing or computing finite element-based functions by exploiting the structure, the low-level structure of those computations. And there are several examples of uses of those factorizations, such as in Bernstein-Bezier, then isogeometric analysis, and then more recently in discontinuous Petrov-Galerkin methods. And so they are quite successful for 3D problems with very high order function approximation. Somewhat tangentially related to this are data reduction techniques in PD constraint optimization, and which is where I come from, where people have constructed adjoint-based techniques through checkpointing the state for evolutionary PDAs. So the state is stored in order to compute the adjoint. And that can be done with logarithmic storage complexity, which is very nice. So people have obviously thought about this quite a bit. And I think we can do a little bit more here on the finite element side. So today I'll talk about two contributions that are complementary to all the related efforts that I've described previously. And these two contributions are go hand in hand. So the first one is we assume that we're given a mesh with a high level of redundancy in the cell shapes, such as the extruded mesh I've shown before, or some other mesh. Maybe it's uniform, maybe it's graded, I don't know. And the first contribution is to detect and exploit these redundancies based on the cell shapes. Now, additionally, and this is a harder task, we would like to enhance the mesh redundancy by moving the mesh nodes. And we don't want to destroy the mesh topology, so these will be our adaptive methods. Our goal fundamentally is to enable clustering of mesh cells into a small number of classes that are based on identity of cells or more broadly similarity. And just so that we know we're not totally crazy, there are actually important ideas in mesh generation and mesh refinement, where people have tried to generate meshes with finite numbers of similarity classes. And so there are some interesting papers here by Suarez and others on computing the number of similarity classes in certain types of mesh generation schemes, such as longest edge bisection of tetrahedra. And they show that this number is finite and it's less than or equal to 37. And so you can, just by considering 37 shapes, you can capture basically any mesh. And so there's definitely hope there, and we're trying to kind of create this structure where it's not available a priori. Now, our challenge is a little bit different because we want to maintain, we're not doing mesh refinement here, we're not generating the meshes. We want to maintain the topology of a given mesh by just moving the nodes a little bit. And we also want to maintain the quality and still create these similarity classes. All right, so there will be two contributions that I want to discuss. The first one's easy to grasp, and it's more of a computer science kind of task. The second one will be on the R adaptivity. So the first contribution is just to detect and exploit the redundancy. So we all know that the cost of storing finite element quantities, such as cell Jacobians, scales linearly with the number of mesh elements. And our fundamental goal with this work is to reduce the order n storage to order m, where m is much less than n. And this will be basically the number of shapes in these similarity or the identity classes that we want to get at. Now, to do this, first we will assume we're given a mesh with its redundant structure, and we just want to exploit whatever is in it. And for that, we will develop a dictionary-based data compression scheme. And the scheme will compress evaluations of basis functions at quadrature points, which of course are linked directly to the geometries of the cells. And as I will show, this dictionary can achieve reductions in storage of more than 99% in key computational kernels. And this enabled us recently to run billion element simulations in under 100 gigabytes of memory. So you can take a high-powered laptop and run billions of elements. It takes a little while, but sometimes people don't care. They can run the simulations for a week or so. All right, so just some finite element background, as much as we need to get all the concepts straight. Here is an important kernel in finite element methods. It's this integral computation. T here is a domain that corresponds to a mesh cell. Here, the phi's are the basis functions, finite element basis functions, and these are some derivative operators applied to those. How do we evaluate integrals? Well, we use quadrature and basis functions on reference domain, T hat. And so we have a mapping between a reference domain T hat here and our physical domain, physical cell T. And it's described by this function here. And then, of course, there's a Jacobian of this. And that's a key quantity that we need to track in these finite element computations. And so we're all familiar with the reference to physical map. And we will use the hats here to denote reference coordinates, and without the hats will be the physical coordinate. All right, so that based on this mapping, we can define the pullback and the push forward operators. And so, for example, the evaluation of a gradient of some function will involve transforming a vector field to reference domain, which requires the application of the covariant transformation. And so that is given here. And that can be done for the entire de Rham complex. So we can do it for H grad, H curl, H div. These operations are a little bit different for each, and they're given here. And back to our original example, if we want to compute the stiffness matrix, for example, in mechanics computations, we need integrals of this type. And then this is on the left, the physical integral, and then on the reference domain, we would compute this integral. And what we need are these transformations, covariant transformations that I've described above. And of course, there's a change of variables, so volume change here. And so if we stare at this integral on the right here, we can now start thinking about memory in finite element codes. So we can only store the reference values, which are very few, and we can then recompute all these quantities every time we need them. So we can either just store the Jacobians or determinants of Jacobians in addition to that, or the inverses, inverse transposes, whatever. Sometimes we can just store the physical gradients in this case. But of course, there's a trade-off here. You can either recompute or you can store more. And so what we're trying to do is store all these evaluations so that the code remains quick, but not do it for every single cell in the mesh, but only the ones that are really occurring uniquely. All right, so that is the main task here. we ran a very simple comparison in a Sandia code called Mr. Hyde, where we played with this trade-off between computation and storage. And here what we did was we stored, let's say 100%, 90%, all the way down to 0, finite element basis functions in physical space. And we compared the basis storage cost to runtime. And you get a curve like this. So, if you don't store anything, your runtime is longer. And what we want to do is basically have this runtime, or better, if possible, at 0 storage. And so actually what we've been able to achieve is this X here. So this is the motivation for the work. All right. Now, for this part of the talk, the basic concept will be just that of cell identity. And so two mesh cells, T1 and T2, with equal Jacobians, must have mappings phi T1 and phi T2, which differ by a constant. So only a translation that is allowed if you want to have them equal. And we say that then these cells have identical shapes. Now, I'm not going to get into cell orientations, which we also have to deal in finite element methods. We will assume for the purposes of this presentation that all cells have been oriented consistently. There's a finite number of orientations, and so usually if you have a lot of redundancy, the different types of orientations don't really matter. You still get the benefits. And so there's a very simple lemma here that if we have finite element basis functions on the reference domain, and these operators, either identity, grad, curl, or div, and then if two mesh cells T1 and 2 have the same shape, the physical values are also equal. The physical values of the basis functions are equal and have equal integrals. And so that's what we're going to exploit here. Here are some mesh examples with redundancy. Let's talk about the two on the right first. So the one in the middle here is actually taken from this electromagnetics application that I talked about at the beginning. And as you can see, there are large clusters of identical cell shapes. And this is due to basically have a lot of the same, these meta atoms that were meshed in the same way. And then on top of that, you get an extrusion in 3 dimensions. And so there's a ton of redundancy. Now here on the left is a different mesh. So this is a structured graded mesh where the cells are not quite identical, but they're identical up to a dimensional scaling. And so our computational infrastructure can make use of that as well. You have to store a little more there, and you also have to account for that in the basis reconstruction, but it is possible and brings significant savings while not hurting the runtime much. So these are the types of meshes that we've been able to achieve huge savings for. Now let's talk about the compression algorithm. So what we do is construct a list of unique cells by looping over all mesh cells Ti and comparing to cell Tj in the list of unique cells that we already built. The distance between cells is computed based on the cell Jacobians. And here is the formula. for the distance, we use the Frobenius norm and compute these differences between Jacobians. And things are normalized in the following way here. And so these sums run over the quadrature points. TJ is the cell that's already in the dictionary, and TI is the cell that we compare to. If this distance between the cells is less than some epsilon, then we say we found a match, and we replace all basis evaluations on TI with those in TJ. In addition to this, we distinguish between lossy and lossless compression. And so we let epsilon naught be the largest acceptable compression tolerance for a given application without significant impact on accuracy. And there's always such a number due to Say's lemma or Strain's lemma. And we say that the compression is lossless when this epsilon is less than or equal to epsilon naught, and it's lossy if it's greater. And so we'll talk mostly about lossless compression for the remainder of the talk. That's sort of the hard case. The lossy compression is a little bit easier from the R adaptivity point of view. That's why we'll hit on lossless. The compression algorithm is actually fairly simple, and I think this could be implemented in FEM or DEAL2 today. Really what we do is just build a dictionary of cells called E epsilon. And epsilon denotes this tolerance. It could be very small if you want lossless compression. And all we do is just compute these distances, and if the distance between Ti and Tj is less than epsilon, we say the match is found, if a match is not found, then we just add this cell Ti to the diction. It's fairly simple. This can be optimized in many ways. The searches could be done more efficiently, but fundamentally, this is what we have now in this code, Mr. Hyde, and this is what brings very significant memory savings. Now let's talk about the compression ratio. So we define it by the ratio of n, which is the number of cells, minus the cardinality of this dictionary, and n. And so this is basically how much you've been able to save on these Jacobian evaluations. And so for a structured square mesh on the left here, we have a lossless compression ratio of 98.4%. And for this mesh with these trapezoidal shapes, which can be traced back to 4 fundamental shapes, we have a compression ratio of 93.75%. And then on the right is a tough mesh, which is a mesh of a circle, which in this case, we can only compress down to 15%. These are just some examples. The second concept that we will need for later is that of a compression curve. And all that is just a plot of the compression ratio as a function of epsilon. So as your tolerance, epsilon, increases here, you will get, of course, 100% compression because everything ends up looking the same. Then there's going to be an area here between 0 and 100%. And then finally 0. And for this mesh of a circle, we observe no compression for any epsilon less than 10 to minus 2, which is kind of obvious by just looking at the mesh. There's not a lot of cells that are the same here. In fact, sure, any really are the same. So that is the compression curve. And then this is just a very simple illustration of the memory savings we got for a heat transfer example on a structured grid of square cells. And so we have a 32,000 by 32,000 mesh of square cells. So that's over 1 billion. We have a compression tolerance of 10 to minus 10. So we're going for lossless compression. And we're looking at memory profiles and timing data on the Mr. Hyde simulation. And we can see that if we don't use any compression, our memory use is over 800 gigabytes here. If we use our tricks, we get to about 250 gigabytes. If we use some additional tricks where we also play with compressing the integration points, we can get down to below 100 gigabytes of RAM for 1 billion elements. And so this is an illustration of what you can get. And we were able to apply this also to the electromagnetics mesh that I talked about originally, and saw similar savings for those extruded meshes with repeated shapes. And that enabled us to run simulations of on the order of hundreds of billions of elements when we solved Maxwell's equations on our institutional clusters at Sandia, which are really not that powerful compared to the state of the art. So that concludes the first part of the talk. Now I will switch to our adaptivity. Any questions so far?
Let's keep going. We'll discuss at the end.
Yeah. All right. So the second contribution is now to enhance the mesh redundancy. We're given a mesh that does not have it. How do we get it? The technique we use is based on our adaptivity and a k-medoids clustering algorithm. And since we're mostly interested in lossless compression, we're going to use a sparsity promoting optimization formulation of the problem. Our optimization formulation is inspired by some recent work that we did on optimization-based mesh correction with volume and convexity constraints. That's a JCP paper. And it's an alternative to some similar schemes that are based on solving the Monge-Ampere equation. I think the schemes we developed are a little bit more robust and can be made scalable very easily. We will have to contend with inequality constraints on the cell volumes to prevent tangling and to ensure mesh quality. And those inequality constraints will be handled using an augmented Lagrangian method, which also scales. And this was published recently in SIAM Journal of Optimization. So basically, we will use k-medoids clustering. We will use a formulation motivated by this work here. And then the algorithm itself, the scalable optimization algorithm, is coming directly out of this ALSQP paper published last year. So that is the preview. So I'll cover the problem formulation and then talk about the algorithms. For the problem formulation, we need to talk about the quantities of interest first, and that will help us define the objective function. So we will focus on quadrilateral elements here with straight line geometry. We think we can accommodate other types of cells and geometries, but I think this is a sufficient starting point. We'll have mesh TH consisting of these cells and vertices P hat given there. And then we'll assume that we have some dictionary B epsilon that we can develop for this mesh. And just keep in mind when we have, the P hat here, that's a given mesh. So it may not have any redundancy or very little redundancy. And whatever dictionary we get, and our goal is to improve that by producing a mesh THR such that this B epsilon R is then significantly smaller than B epsilon. But we have to maintain topology, and we want to do as little mesh motion as possible. And so we'll have some constraints. The optimization variables will be vertices P, and we'll have this double indexing scheme here. All right, so now we have to develop a notion of distance here, so we have to look at some Jacobians. What we decided was easiest and most efficient in the quadrilateral case was actually to split the quadrilateral into two triangles using vertex index triples 1, 2, 4 here and 3, 4, 2. And based on this splitting, we can then define Jacobians for each of the triangles. And here they're defined by these quantities C and D. And then the two triangle Jacobians can be put into a row vector that we denote here by K that has 8 entries. And so these are all the Jacobian entries for the two triangles. And that in some sense defines the shape of this quadrilateral for us. Now for each cell, Ti, we will also associate a target shape, mu I, that we want. So those will be these shapes that we can compress down to. And those will be also vectors with 8 entries, analogous to this Ki. And what we want to do with this optimization is reduce the misfit between K of P and mu, where these are matrices in n by Rn by 8. I haven't told you how to define the mu's. I'll tell you that in a second. So how do we define the objective function? Well, I said we want to focus on lossless compression, and so ideally this is a sparse matching problem in which we're trying to maximize the number of 0 rows in the quantity K of P minus mu. So these are, our Jacobians, and these are our targets. And there are approaches that solve this problem. They are based on the concept of group sparsity. There's a nice paper here by Buck and others. And they use the mixed L1 LQ norm. And here is one such quantity. You can plug in 2 here for Q, for example. But the problem with these quantities of interest is that they are non-smooth, and that is due to the norm. And so they can be quite difficult to handle algorithmically, and we're not aware of scalable approaches to directly attack this quantity of interest. Now, in contrast, you can just do little L2 squared minimization. This is a smooth function. It's relatively easy to minimize using derivative-based methods. But the problem with it is that any notion of group sparsity may be lost. So you're not targeting, maximizing the number of zero rows at all. This is because the misfit across all these quantities is basically smeared across the entire mesh. And so you will reduce this misfit, for the whole mesh, but none of them will be actually close to zero. And so, as I said, no zero misfit. So you get no lossless compression unless, and you notice this on a structured mesh, this quantity is zero for all I, for all cells. So this is a challenge, but it also motivated an idea that we had. And that was that instead of solving this non-smooth problem, we can solve a smooth problem as long as we identify a subcell of indices Z out of this set, such that Ki of P minus mu I equals 0 is achievable in some sense for all I in this set Z. And so given such a set, then the functional to minimize is just the L2 squared norm functional, but now over indices that belong to the Z set, and that leads to our main objective function, the lossless objective function that I've given here. And note here that these alpha i's are binary. So they can be 0 or 1. And that is decided based on whether they are members of the set Z or not. So, of course, the difficulty here will be identifying these alpha i's. And to do that, we will develop a procedure that's also based on a relaxed version of this function, objective function, which will be the version where alpha i's are just in R0 plus. So what we will do, just as a preview, is sort of a ranking of cells based on this objective function, and then we'll zoom in on this the alpha i's, the binary alpha i's, and solve this lossless problem. Now, in addition to the objective function, we need to worry about constraints. We want minimal mesh modifications. We don't want tangling or cell inversion. And so what we do, and this is just one thing you can do, but there are a few others, we restrict the volume change for each mesh cell by some percentage, like 10%, 20%, or whatever. Optionally, we can maintain cell convexity directly, which is what we've done in the 2016 paper. In addition, you can eliminate all the nodes that define important geometric features. So you may have your boundary of the domain, and you may have some important geometry inside, and you want to get rid of that. We will eliminate those and simply not use them as variables. The constraints are defined using the quantities Vi of P, which are the volumes of the cells. And they are, for the quadrilaterals, given by the shoelace formula, which we give here. And so these volumes will form our set of constraints. And in addition to that, we will look at the minimum volume over all cells and the maximum volume over all cells, given by the original vertex configuration P hat. And we will define the lower and upper volume bounds in two ways. using global quantities where we just use these mins and maxes, where we multiply them with some factor. So 1 minus gamma or 1 plus gamma. Gamma is between 0 and 1. So you can compute these things on the entire mesh and then say, I want something between 90% and 110% of that volume for all the cells. Or you can use local quantities, which is important if you have meshes with the big difference in the smallest and largest cells. And so in that case, you just use the previous volumes for each cell to define your bounds. All right. And so then what we finally arrive at is this optimization problem where we minimize the objective function L of P, and that can be either the lossless one or the relaxed one, subject to the volume bounds. And as I said, we can replace these with convex T constraints and other types of constraints. This problem has a solution because the feasible set that's defined here in 1b is non-empty for both definitions of bounds here. And that's easy to see if you just plug in P hat, which is the original vertex configuration. All right, so now let's talk about the algorithms. So this is the optimization problem. What are the missing ingredients? Well, we need an optimization method to solve it. But in addition to that, we also need to define the mu i's, here the targets, and we need to define the alpha i's, which are these binary weights that we ultimately want. I will go through the optimization algorithm first and then talk about a clustering algorithm that we use for the cell targets and the bracketing algorithm for the weights. All right, so for the optimization, we use recently developed ALSQP method, which is an augmented Lagrangian penalty method. And a unique feature of it is that we use the augmented Lagrangian for the inequality constraints. In this method, general inequalities are transformed to equalities and bounds using slack variables. And so we transform the problem that I had on the previous slide into this problem. So we just have an equality constraint now with the slack variable s, and then we put bounds on the slacks. Then the subproblems that are solved in this ALSQP method penalize these inequalities. And the way that is done is, for the bound constraints in this case, is through very simple min-max operations. These are just chopping operations. And this is the penalty that is added to the original objective function. And then we're left with equality constraints only. And so the idea is then to solve a sequence of equality constraint optimization problems using sequential quadratic programming methods, SQP methods. I'll note here that the objective function is actually differentiable despite these max-min terms here. And one can even come up with a notion of a Hessian of the for this objective function using some semi-smooth concepts. So that's why an SQP method, sequential programming mapping, is justified. All right, so the subproblem solver is a method that I co-developed with Matthias Eigenschloss some time ago. It's a composite step trust region SQP method. I'm not going to spend a lot of time on it. I'll just say that the way it works is that we aim for the satisfaction of the constraints first. So these are the equality constraints here in 2B. And then we improve optimality while staying in the null space of the linearized constraints. And sorry for the change of notation here. X is just an optimization variable, not the vertex coordinates. And so we have this quasi-normal step, Nj, that takes us toward the linearized constraint, and then we take a tangential step, Tj, that stays as much as possible in the null space of the linearized constraint while trying to improve optimization metrics, so reducing our objective function. And that is done based on a quadratic model of the Lagrangian. So this is where quadratic programming comes in. Now, the key computational kernel in this method is the solution of a so-called augmented system, which looks like this. So we have an identity here in the 1-1 block, and then we have the Jacobian of the equality constraint in the 2-1 block, and it's transposed in the 1-2 block. And so that is the only system that we need to solve in these types of methods. And it goes basically in all the different steps of the method. In this specific application, this augmented system matrix looks as follows. So we have, again, an identity block here, and then we have the Jacobian with respect to the vertices, and then Jacobian with respect to the slack variables. Now, these are just negative identities because our constraint is just V of P minus S equals 0. So that's a very simple structure. And then, and this is really key, because we define these volumes by the shoelace formula, the entries of G prime P take this form. And this resembles discrete divergence on the mesh. And then the transpose of it, which goes in the 2-1 or 1-2 block, is just the discrete gradient. And so if you were to form a Schur complement of this augmented system matrix, you get this. And so this is a perturbation of the identity by a discrete Laplacian. And so in the examples that I will show, this augmented system is super easy to solve just using non-preconditioned min-res or GM-res, because this is just a perturbation of the identity. There are other problems where we have some large domain length scales and where this term may dominate. And in that case, well, you can just use multigrid, and that can be very, very effective. And one note about the previous algorithm is also that it handles inexact solves of this augmented system. In fact, and we have, I apologize, and we have developed mechanisms to handle that inexactness based on the progress of the optimization method. All right. Okay, so to define the targets, we use k-medoids clustering. This is very simple if you're familiar with k-means. It just uses sort of a vector version of it, and it is based on the fact that medoids are representatives of a data cluster, which minimizes distance to all other points in the cluster. And so I'm not going to go through the algorithm. It's fairly simple and it's quite efficient. So to compute the binary weights, we have two phases. And this is why I talked about a lossless objective function and a relaxed objective function. The first phase is to rank misfits, and this just basically allows us to determine the best candidate cells for lossless compression. So we will solve this super easy optimization problem with weights in R0 plus, and then rank the cells by the misfit that they achieve. After that, we will use a bracketing phase to zoom in on the losslessly compressible cells. And so the key here is that in the bracketing phase, we employ a bisection procedure that's based on the percentage of cells for which we have conjectured near zero misfit. And so, as I said, we compute the weights by sorting the cell misfits first in ascending order, and then we just say we guess 50% of them are lossless. If the objective function is very small, it means we're on the right track, and we can increase that to 75%. If the objective function is large, it means we probably don't have all lossless cells. We will decrease it 25%. And the process is then repeated. And so because this is a logarithmic complexity procedure, you can zoom in very quickly in just a handful of steps within 1% accuracy of the lossless set. All right. This is just for posterity, the bracketing algorithm. Sorry for using the references from our preprint, which I will reference later. But basically, what it consists of is a ranking phase, which uses this relaxed objective function LR, and then it switches to this bracketing phase, which uses the binary weights and the bracketing procedure. So that's roughly the sketch. And in all of these steps, we use ALSQP to solve either the relaxed optimization problem or the one with the 0, 1 weights. All right. Okay, so now to some numerical results. The first example is just the recovery of a structured mesh. And so what we do here is just start with a uniform mesh, which we perturb, and we just perturb the interior vertices by a fairly large amount here. And then we try to basically recover the original mesh because we know that that would be, the ultimate optimal answer in this case. The volume constraints are formulated using the global bounds here, because we're using fairly large perturbations. So we say we want to be within 40% of the global min and max in the volumes. And that will basically allow for the entire mesh to relax to a single cell. The algorithmic parameters are 10 to minus 10 for the epsilon for our, this is the tolerance for the compression, epsilon. Tau is the tolerance for ALSQP. So we solve these problems down to very small tolerance in terms of the optimization, just because we can. And there are a few other parameters for the how many ranking cycles or bracketing cycles we want. And the ALSQP parameters are all taken from our 2023 paper. All right, so here are the results. So the mesh before is given here. The mesh after, of course, is fully uniform mesh. If we can't do that, we can't do anything. Here on the bottom left, I'm showing the first cluster assignment, and then on the next to it is the last cluster assignment. we chose to have two clusters here just for fun. You can have one or two or four. This is just to test the algorithm. There are changes, of course, in the assignments, as you can see, maybe especially in this region, so on. Now, we talked about a compression curve, and here I'm plotting the compression curve for the original mesh in blue. You can kind of see that it goes like that, and there's very little compression past 10 to minus 2. After we're done, we're basically down to nearly 100%. This is the red curve, which is what we would expect for the simple case. Another thing I'd like to point out is the log 10 misfit with respect to the cluster medoids. And so these numbers, so this is log 10, so this would be 10 to minus 21, 10 to minus 22, 10 to minus 23. So that is the level of objective function we get. So these are individual cell misfits from the medoid. And so very, very small. Now, this is sort of a boring example, but it allows us to study the scalability of our algorithm. And here are some iteration counts for a sequence of meshes going from 20 by 20 to 320 by 320. CLS here is the total number of clustering stages. AL is the total number of augmented Lagrangian iterations. SQP is the total number of SQP iterations. And then CG is the number of projected conjugate gradient iterations that mark the tangential step computation, which is the key computational kernel in SQP. And then here in the last column, I have the average number of GMRes iterations per call to GMRes. And so what's interesting here is, first of all, that all of these numbers stay in narrow ranges. There's no perfect scalability, but we're also using random meshes, so it's a little bit difficult to kind of nail that fully. But all of these numbers, except for the very first number, are narrow ranges. And then also this average number of GMRes iterations goes down actually to roughly 3. And that has to do with this perturbation of the identity by discrete Laplacian. And so that's good to observe. Now, a more challenging example is square mesh with poor topology. So we have a 10 by 10 boundary division mesh, but only 99 quadrilaterals in the interior. And so this was a mesh that was giving us trouble in the early stages of the project. We tried to come up with sort of optimal ways just by hand, what a solution would look like. And so you can kind of see that maybe you could straighten out this section and get a rectangular mesh with roughly the same cells. So that was my guess is what the algorithms would do. In this particular case, we also use 2 clusters, and we formulate the constraints using the local bounds. Unlike in the previous case where we used the global bounds. So here are the results. They're quite interesting, not what I thought that they would do. So this was the mesh before. The mesh after is given here. And so it created basically this big parallelogram region here, and then some other parallelogram regions here and here up on top. And I think what best illustrates the power of this algorithm is if we look at the log 10 misfit with respect to the cluster medoids. Anything in blue here is around 10 to minus 20. And so all of these cells here were compressed down to 10 to minus 20 misfit. And so we have one medoid, one cell representative for this entire region, and then we have one for these 2 regions. And so this also illustrates how this works for multiple clusters, and there doesn't need to be any sense of kind of geometric proximity. Sort of just works automatically. Now, in terms of the compression ratio, we get 68% here. 68% lossless. And we started with something that was fairly poor. So that's that example. And then finally, the circle mesh. And this is just a slightly larger example. We use 4 clusters. We formulate the constraints, again, using the local bounds with 40% deviation on either side. And this is what we get. So basically what the algorithm does is creates this large center region, and we kind of thought it would do that, where it straightens everything out and makes all the cells. They're actually parallelograms. They have a slight slant. Again, if we look at the log 10 misfit, we see this large region with nearly 0 misfits, 10 to minus 25 or better. We also see 3, so we had 4 clusters. So this is one cluster, and those are the medoids, because they're all the same of that cluster. And then we have 4 other medoids that they compressed all the way down. But in those clusters, of course, you only can get a single 0 misfit, because all the cells are, in fact, different. So that's that. I do want to mention in this particular case that we can do better by looking at other objective functions that may include scaling, dimensional scaling, and maybe even rotations. Now, of course, then the compression and decompression of the finite element-based functions gets a little bit more expensive, but that's something to consider in the future. Right, and then to conclude, we've demonstrated 2 complementary approaches that reduce the memory burden for finite element simulations. The first contribution was this dictionary compression scheme, and we've seen very large reductions in memory use with the Mr. Hyde finite element simulator. The second contribution is the R-adaptive mesh optimization. There we combined the ALSQP method with k-medoids clustering and a bracketing procedure. With that, we demonstrated significant lossless compression for many challenging meshes, and we managed to maintain cell shape quality through volume inequality constraints. In the future, we can think about convexity constraints, which I think make a lot of sense in many applications. And we can speed up these algorithms quite a bit, I feel. And then finally, a note on the super large scale setting. When you have meshes that contain millions or billions of finite elements, these algorithms are really meant to be applied to subdomains that result from typical spatial decomposition rather than the full mesh. You probably don't want to try to compress a mesh with 100 billion cells. You just need to compress maybe parts of it that have 1 million or 100,000 cells. Because if, even if you have, let's say, 1,000 of these cell similarity classes in a 1,000,000 element mesh, you're still compressing down to 99.9%. So the idea is to apply this to smaller chunks. And I will close with the references. And that is it. Thank you. So the material property changes across a cell. Is that what you're saying?
Correct. Yeah.
Then do you partition the cell according to the material then?
Sometimes yes, sometimes no.
So I think it would sort of depend, yeah, on kind of what is your scheme there.
Yeah, okay.
Um, oh, I mean, that's an interesting question. I haven't thought about multi-material meshes, but I would imagine that something could still be done, but yeah, I don't know.
Yeah, well, yeah, and obviously if you have large areas where it's all the same material, it would still work. And so
Yes,
you might end up, with a less efficient boundary, between materials, and you'd still be able to get a lot of the benefit out of it. I was just curious if that
yeah,
had been a thing.
I mean, that's right. If you have a lot of islands, little islands, then I think it may get difficult
Yeah,
because basically you need to capture that geometry, right?
yeah.
Uh, and the way this scheme works is you can place points on the geometry you want to preserve, and so we will not move those. We'll move everything else,
Hmm.
so all the voids and things like that.
Yeah,
But of course, yeah, the efficiency depends on sort of the ratio of all the little geometric features to the voids between.
right. The more the original mesh looks like a perfect, mapped rectangular mesh, right, the better it works.
Sure, of
But
course. Mhm.
but you can still get something based on, as you say, the subdomains, the
Right.
individual areas. Yeah, that's really neat. Thank you.
Thanks for the question.
Okay, other questions?
Hi, Dennis. It's Misha here. Do I understand correctly? There is clearly some connection to what we did with you, right, 10 years ago about optimization and fixing volumes, right? Is it the same thing, similar thing?
So the optimization algorithm has evolved since we can handle inequality constraints much more efficiently and much more rigorously because in that paper we just slapped on a penalty, which wasn't always working. In this case, we can actually solve the optimization problems using this ALSQP method much more robustly.
Okay, an actual question, if you look at these meshes, do I understand that essentially you're trying to make volumes the same?
Yes, we're trying to make the shapes the same, which also makes, of course, the volumes the same. But
Right.
uh,
How do you know that it's unique solution? This it was, I think, was bothering me from very beginning. You can.
so there is no unique solution, and we cannot guarantee that because our constraints are not linear. And so even though the objective function is quadratic, the constraints are nonlinear. And so you can get many solutions. And in fact, we do, especially on this circle mesh that I showed last, depending on sort of where we start, you can get different solutions. I mean, they're all still valid, but they're not unique. No.
I think it would be very interesting to have a mesh of 5 cells, something, where you can see and, more clearly what can happen and see what kind of meshes you can get, especially with respect to your compression stuff.
Yes, yes. The smallest one we studied was this one with 99 cells, but I agree that we should probably scale it down even further just to see all the possibilities.
Yeah.
Yeah.
But anyway, thanks.
Thank you.
Thank you, Misha. I mean, we do mesh optimization for different reasons. And
Yes.
if you look at the two meshes on the top,
Mhm.
I think you can argue that maybe the one on the left is better from symmetry, from simulation perspective, and the one on the
Yes,
right
it has,
probably
yeah, and it has better quality. You can
right.
see by this blue curve, which is the compression curve before the optimization, it's actually crossing over here. kind of informs you also of the quality. So yes, I agree with you. What I think we should do is, instead of those volume constraints, or in addition to them, and I think they could even be combined, we could consider convexity constraints.
Right. So
And yeah,
I was going to ask if you thought about combining the two, since they're both.
that's a very good question. I think they could be handled in one shot, because the shoelace formula is using basically the triangles, right? And the convexity constraints can also be formulated with 4 triangles in a quad. And so that's what we used in the 2016 paper with Nisha and others. And I think we could basically use positivity of those oriented triangle volumes, and also constrain them so that they don't go too far. And so kind of kill 2 birds with 1 stone. So yeah, I think
Okay.
that's possible.
And kind of follow up on this, 3D. Have you done any general 3D?
So we've applied the dictionary scheme to 3D, but we haven't tested this our adaptivity method on 3D. Yeah,
Because convexity on 3D hexes, I think,
that
it's very, very restrictive.
it is. It's quite challenging. Yeah, I don't have, a good answer for that.
Okay.
But and we haven't tested this specific algorithm on. I think I tried just something like a perturbed yeah, I think it was a random grid, but no, we only have some results from actually the dictionary scheme.
Yeah, thank you. Other questions for Denis?
Can I ask one more question, Denis? What about polygonal mesh in 2D? Clearly, you will need some convexity, because it's much more degrees of freedom, and your optimization can lead to some inverted or whatever.
So polygonal elements don't have a reference element in well-defined Jacobian unless you subdivide.
Okay, what about triangular meshes?
Oh, so the triangular meshes are fine. What you will end up seeing in triangular meshes are, when we do this compression, sort of like strips of things that get, because they all have sort of different orientations, but you can kind of get strips of sort of checkerboard-like patterns with the triangles.
By the way, polygonal meshes clearly have some reference with respect to each corner. You still can deal with kind of this one.
I guess anyway, we find a reference cell, but I'm not sure that that's really, people who do general polyhedral finite element methods, I'm not sure they use the concept of a reference element. I don't know. Sandia, maybe you know better about that.
Well, I mean, maybe somewhat related. How about higher order curved elements that can still have an interesting shape and have a well-defined Jacobian that is complicated?
Super high order, super distorted. Is that what you're?
Yeah, or something like, you know what I'm talking about?
I think I do.
Have you guys thought about that?
Briefly, yes. I think the issue is, in that case, it's a balance between, because you have a very, very high order element in that case, right? And you want it to be that, and you want it to be distorted. So I'm not sure how many of these similarity classes are really, possible, because you're kind of going against that with all these distortions. Now, what I've been thinking about is usually the meshes get distorted due to some field that's based on the physics in some sense, right? And can one maybe store the distortions rather than all the elements and all the associated quantities? Although then one has to reconstruct the basis functions and derivatives. So I don't know, maybe there are better ways to compress them. One question I have for you is in FEM, do you guys have some compression schemes already, and other than the matrix-free sort of assembly?
Not like this. Not on clustering by the Jacobian. This is
Okay.
This is one reason this is interesting for us.
Okay.
It makes some sense.
Have you used the ZFP compression for field quantities at all?
Who is the question for?
Well,
me?
I guess actually it's for either. I mean, I'm just curious how that compares.
Yeah, we have, but that's kind of orthogonal to this.
No, it's true. You could use both, right? In theory.
Yeah.
Yes.
Yeah.
Actually, at the beginning of this project, we did spend some time looking at those schemes, and even for the meshes. Yeah, I think you can just combine it. I don't know what kind of have you been able to get decent compression out of those schemes, Sandia?
Yes, for the fields.
For the
Yes,
fields, yeah.
For the fields, you can.
Yeah, because I do get the question about the fields quite a bit. So good.
It depends on the problem, obviously, but if you have regions where the field is essentially constant or close to constant, then you do get a big compression, of course.
Good.
If it's highly turbulent everywhere, then maybe not.
Yeah, I mean, sure. And similar here, if you have millions and millions of objects whose boundaries you have to track very carefully, you're not going to get a huge benefit out of these schemes either. But they certainly apply for a lot of other scenarios.